Black holes, the most mysterious objects in the universe. Black holes are among the most enigmatic and awe-inspiring phenomena in the cosmos, challenging our understanding of physics, space, and time itself. Born from the catastrophic death of massive stars in supernova explosions, black holes represent regions in space where the gravitational pull is so intense that nothing, not even light, can escape their grasp. At the heart of every black hole lies a singularity, a point of infinite density where all known laws of physics cease to operate, surrounded by an event horizon, the boundary beyond which no information can return. These cosmic giants vary in size, from stellar mass black holes formed from individual stars to supermassive black holes found at the centers of galaxies, including our own Milky Way's Sagittarius A*, which contains millions of solar masses packed into a volume smaller than our solar system. Despite their invisibility, black holes can be studied through their interactions with nearby matter. Accreting gas and dust emit intense X-rays as they spiral inward, and by the gravitational waves they produce when they merge, phenomena first detected by observatories like LIGO and Virgo. The idea of a black hole dates back to the 18th century with thinkers like Jean Michel and Pierre-Simon Laplace, but it was Einstein's general theory of relativity in 1915 that laid the theoretical foundation, later expanded upon by physicists like Karl Schwarzschild, who discovered the first exact solution describing a black hole, and Stephen Hawking, who introduced the revolutionary concept of Hawking radiation, suggesting black holes can emit particles and eventually evaporate. Yet, these revelations only deepen the mystery, especially regarding the information paradox, the question of whether information consumed by a black hole is truly lost, which contradicts quantum mechanics. Black holes also play a pivotal role in galaxy formation and evolution, possibly regulating star formation and helping to shape galactic structures. They stretch the limits of human comprehension, blending science fiction and fact as they warp spacetime, freeze time at their edges, and may even connect to other parts of the universe through hypothetical wormholes. Observational breakthroughs, like the first direct image of a black hole's shadow captured in 2019 by the Event Horizon Telescope, have confirmed long-standing theories and opened new avenues for inquiry, yet have also emphasized how much we still don't know. The study of black holes touches every corner of physics, from thermodynamics and quantum theory to cosmology and relativity, and each discovery brings more profound questions. Could black holes be the key to unlocking the unification of general relativity and quantum mechanics, a theory of everything? Are there primordial black holes from the early universe that could explain dark matter? Might we someday harness their immense energy or even use them for interstellar travel? While definitive answers remain elusive, one thing is certain: black holes are not merely celestial oddities but essential components of the universe's grand design, reminding us that the cosmos is far stranger and more wondrous than we ever imagined. Black holes, long shrouded in mystery and the subject of fascination, become even more enigmatic and captivating when we move beyond the basics and begin to unravel the deeper complexities in the second and final stages of understanding them, where physics, paradox, and cosmic wonder all collide. Once formed, typically from the collapse of a massive star at the end of its life cycle, a black hole becomes a region of space where gravity is so intense that nothing, not even light, can escape its grasp. While the basic premise is already astonishing, it's the consequences and deeper implications of black holes that elevate them to the pinnacle of cosmic mystery. In the second part of Understanding Black Holes, we examine not just how they form or their surface features like the event horizon, but what lies beyond, inside, and even in their interactions with the universe at large. First, consider the event horizon, the boundary around a black hole beyond which no information can escape. Theoretically, once an object passes this boundary, it's lost to the outside universe forever. Yet, this creates one of the most famous paradoxes in modern physics, the information paradox. According to the laws of quantum mechanics, information cannot be destroyed, yet when matter falls into a black hole, it appears to be erased, violating this fundamental rule. This has led to decades of debate among physicists, with contributions from Stephen Hawking, Leonard Susskind, and others who proposed concepts like black hole complementarity and the holographic principle, the latter of which posits that all the information absorbed by a black hole may actually be stored on its two-dimensional surface, challenging our very understanding of space and dimensionality. Then there's Hawking radiation, a theoretical process proposed by Stephen Hawking in the 1970s, which suggests that black holes can emit tiny amounts of thermal radiation due to quantum effects near the event horizon. Over immense timescales, this radiation could cause black holes to shrink and eventually evaporate, providing a theoretical mechanism by which information might be released, albeit in a degraded or scrambled form. Still, this radiation remains undetected, and its existence, though mathematically sound, has yet to be empirically proven, keeping the mystery alive. Moving deeper into the second part of black hole exploration, we encounter the concept of singularity, the core of the black hole where all its mass is thought to be concentrated. At the singularity, the curvature of spacetime becomes infinite, and known laws of physics break down. General relativity predicts this infinite density, but quantum mechanics cannot cope with it, signaling a profound gap in our understanding, a sign that a unified theory of quantum gravity is desperately needed. This leads researchers to string theory and loop quantum gravity in the search for models that can reconcile these seemingly contradictory realms of physics. Meanwhile, rotating black holes, or Kerr black holes, add another layer of complexity. Unlike static Schwarzschild black holes, Kerr black holes possess angular momentum and feature a region known as the ergosphere, an oblate spheroidal area outside the event horizon where spacetime is dragged around by the black hole's spin. In theory, energy can be extracted from the ergosphere, a concept proposed in the Penrose process, which hints at potential futuristic propulsion or power systems. Furthermore, the existence of extremal black holes, which carry maximum possible charge or spin, pushes the boundaries of our mathematical models and raises questions about stability and physical realizability. As if that weren't enough, some models suggest that black holes could serve as gateways to other regions of the universe or even other universes entirely. This leads to the speculative but intriguing idea of wormholes, which could theoretically allow travel across vast distances in space and time. Although wormholes remain purely hypothetical and no evidence of them exists, they arise naturally in solutions to Einstein's field equations under certain conditions. In some versions of the multiverse theory, each black hole might even spawn a new universe on the other side, an idea that turns black holes from cosmic tombstones into cosmic birthplaces. Additionally, the concept of white holes, the time reversal of black holes, which expel matter but cannot be entered, has also emerged in theoretical models, though no white hole has ever been observed. As we near the current frontiers of black hole research, gravitational waves become a pivotal area. First detected in 2015 by LIGO, these ripples in spacetime confirmed Einstein's century-old prediction and opened a new era of observational astronomy. Many gravitational waves detected so far have been the result of black hole mergers, allowing scientists to probe their properties indirectly, measuring their masses, spins, and even testing general relativity under extreme conditions. In fact, some of the most massive stellar black holes have been identified through these signals, showing that black holes may be more massive and more numerous than previously thought. On a cosmic scale, supermassive black holes, millions or even billions of times the mass of our Sun, reside at the centers of galaxies, including our own Milky Way, where the radio source Sagittarius A* has been confirmed as such a behemoth. How these giants formed so early in the universe remains a mystery. Did they grow from the merger of smaller black holes, from direct collapse of massive gas clouds, or from primordial black holes born in the moments after the Big Bang? These questions are still open, and their answers may unlock secrets about galaxy formation and evolution. Recent breakthroughs, such as the Event Horizon Telescope's imaging of the black hole in the galaxy M87, provide visual confirmation of black hole properties predicted by general relativity, like the photon ring and shadow, but also raise new questions about magnetic fields, accretion disks, and relativistic jets, which spew particles at near-light speeds from the regions near black holes. These jets, despite originating in an environment where escape seems impossible, are among the most energetic phenomena in the universe and play a critical role in shaping galactic environments. On the observational frontier, astronomers continue to seek black holes using indirect methods, studying stellar orbits near invisible companions, X-ray emissions from accretion disks, and microlensing events where black holes bend background light due to their immense gravity. Some researchers are even hunting for intermediate mass black holes, the long-sought missing link between stellar and supermassive black holes, believed to reside in globular clusters or dwarf galaxies. At the same time, the idea of primordial black holes, hypothetical relics from the early universe, gains traction as a possible explanation for dark matter, the elusive substance that makes up about 27% of the universe's mass-energy budget. If primordial black holes do exist, they could reshape our understanding of the cosmos and its composition. In the most cutting-edge theories, physicists are even exploring whether our entire universe could be inside a black hole, an idea that stems from the similarities in mathematical structure.